Hey class, in today's note we'll be taking a look at Charles's law, one of the three first gas laws you'll be learning in your Unit 5 gases. That's your title. I'll give you a couple seconds to write it down. History. In the late 1700s, French scientist Jacques Charles started to study the relationship between temperatures and volumes of a fixed amount of gases kept at a constant pressure. Using his data, he concluded that the temperature of a gas is directly proportional to its volume. This means that, for example, if the gas temperature rises, then the volume of the gas will also rise with it. Using his data, he also developed a formula. Now, some applications of this are, you can see this law work with bicycle tires. As the more you heat the air inside a tire, the bigger the tire will expand. That's why they will sometimes have writing on the tires that says to inflate the tire to X amount of pressure when cold, so that you don't overinflate the tire and it doesn't burst on you while you're riding in a hot summer's day. Next slide in 3, 2, 1. Charles's law. The relationship between the volume and temperature of a fixed amount of gas kept at a constant pressure. Here is your formula. V1 over T1 equals V2 over T2, where V1 and T1 are the volume and temperature of a gas before a change, and V2 and T2 is the volume and temperature of the gas after a change. Now, when using the formula, the temperature must be in Kelvin, and you might ask why. Well, let's say I was using a temperature scale that had negative values, like degrees Celsius. Well, if one of my temperatures were negative value, like let's say negative 20 degrees Celsius, and my other temperature was a value of, let's say, something over 0 degrees, like 30 degrees Celsius, well, I would end up solving a volume which is negative. Now, as you know, volume can't be negative, so we use a temperature scale that does not have any negative values, such as Kelvin. Now, the volume can be in any unit as long as both sides are the same, otherwise you'll have to convert. And pressure can be in any unit as long as the pressure doesn't change throughout the situation. Next slide. The next two slides will be examples. In 3, 2, 1. Example 1. The air in a room is 299 Kelvin, and a balloon with a volume of 500 milliliters is brought from the room outside to this 274 Kelvin air. If the temperature of the air in the balloon dropped to that of the outside air, assuming the pressure didn't change, what is the new volume of the balloon? Okay, so I know volume 1, it tells us that the volume of the balloon before moving outside and changing temperatures was 500 milliliters. So I'll write that down. I also know the temperature inside the room, which was before the air in the balloon changed temperature. It told me 299 Kelvin. And I also know the temperature after the balloon was brought outside into the colder air, 274 Kelvin. That means I do not know volume 2, and that's what I'll be solving for. Okay, I'll write down my equation. V1 over T1 equals V2 over T2. I'll rearrange for the variable I'm solving for, which is V2. That means T2 will go on the top of the other side. So V1 times T2 over T1. I'll substitute my values in. Volume 2 equals V1, which is 500 milliliters, times temperature 2, which is 274 Kelvin, all over temperature 1, which is 299 Kelvin. The kelvins will cancel out. I'll put this onto my calculator and get a value of around 418.19 milliliters. There we go. Moving on to the next example in 3, 2, 1. Okay, example 2. A balloon is 2.3 liters in a room at 275 Kelvin, and the balloon is taken outside where the pressure is the same. What temperature in degrees Celsius is the balloon if the balloon's volume is measured to be 2,740 milliliters? Okay, so looking at this question, it tells us the volume 1 which is the volume of the balloon beforehand, which is 2.3 liters. It also tells us temperature 1, which is 275 Kelvin, the temperature of the air inside the balloon before it was taken outside. It's asking for temperature 2, what temperature in degrees Celsius is the balloon. So we do not know that. And it also tells us the balloon's volume outside, which is 2,740 milliliters. Now, before I put these three variables into an equation, I noticed that my volumes are in two different units. I'm going to convert volume 2 into liters. This is going to be 2.740 liters. And then I'm going to substitute into the equation. So let me write my equation down. Volume 1 over temperature 1 equals volume 2 over temperature 2. I'm going to rearrange for the variable I'm solving for, which is temperature 2, sorry. That means temperature 2 is going on this side. Volume 2 is staying on this side. Temperature 1 is going to multiply with volume 2, and volume 1 is going to be divided by all that. So now that I have the equation, I can substitute my values in. Volume 2 is said to be 2.74 liters, 2.740 liters, times temperature 1, which was said to be 275 Kelvin, all over volume 1, which is 2.3 liters. Okay, now I plug all that into my calculator, and I get a value of around 327.61 Kelvin. Now, I'm not done yet, as the question asked me the temperature of the balloon in degrees Celsius. That means I'm going to have to make a conversion. So 300, and if you don't remember how to convert Kelvin to degrees Celsius, remember that you're only adding or subtracting 273.15. And this is in Kelvin. To get back into Celsius, I'm going to subtract 273.15. That means my temperature 2, as my final answer, will be 54.46 degrees Celsius. Okay, thank you for watching the note on Charles's Law.